PC.
Okay, so let's try that. All right, technical difficulties. Hopefully this is recording now. So yeah, we're looking at this problem. We normally would think that partitioning an interval into 3 pieces would be worse than splitting it into 4 pieces. Now that we've had lots of time to think about it, let's see if we can come up with something. Does anybody have a suggestion for an interval?
Since we divided into 3 and 4, I was thinking
12?
0 to 12.
Okay, 0 to 12. Okay, that's fine with me. So we'll divide this thing into 0 to 12. Okay, and then we need a function. Has anybody thought about the function yet? And we want the UP3 of f. So P3 would be breaking it into 4 and 8, right? We would like the upper sum, which is this calculation right here, to be better than the upper sum if we use 4 pieces.
If it's smooth, then the smaller. If it's a smooth function, then the smaller, the partition with more pieces is better.
Is going to be better, right? Yeah. So you don't want that. You can't just use a nice function like a line or something. It's not going to work. It's not going to work. Can we do something? Can we do something where we actually would have UP3 of f being exactly the right answer for the integral? Because then you can't do better than that.
If it's piecewise in 3 parts, right?
Okay, if you did something like this, right? Piecewise, I don't know, with 3 pieces. Because now your big M1 is here, your big M2 is here, and your big M3 is here. Right? You're taking those 3 numbers and you're multiplying by the width. The width is 12 minus 0 over 3, which is 4. So you have a width of 4 and a height of big M1. Then another width of 4 and a height of big M2. And then another width of 4 and a height of big M3. That's going to be exactly right, isn't it? Okay, so let's just make up something here. Let's define f of x to equal, now let's just say these numbers are 1, 2, and 3. Okay. 1 if x is between 0 and 4. 2 if x is between 4 and 8. And 3 if x is between 8 and 12. Now, be careful though. I cannot make all of these intervals closed because the function has to be defined properly at the endpoints. So I need to open, you could open here, for example, and open here maybe, something like that. It really doesn't matter. So in other words, you're putting an open circle on the ends of these. But the big M values are still exactly what we said they were. The idea here is that with this function on this interval, UP3 of f is exactly the correct value of the integral from 0 to 12 of f. It gives us the exact right value. You guys agree with that? Because we know what the exact right value is. We know the exact right value is this area plus this area plus this area, right? That's just 3 rectangles. They each have a width of 4, and the heights are M1, M2, and M3. So it's exactly this expression up here, right? But then if you try to chop this thing into 4 pieces, right? If you chop this interval into 4 pieces, what will be UP4 of f? Well, of course, you're going to have 12 minus 0 over 4, b minus a over n. But now, your big, okay, so the first big M1 would be equal to 1, right? But then big M2, which goes from 3 to 6 here, big M2 would be 2. And big M3, which goes from 6 to 9, would be 3, and big M4, which goes from 9 to 12, would also be 3, you see. So you would end up getting 3 times 9 here, which would be an area of 27. But what is the area supposed to be? It's supposed to be 4 plus 8 plus 12. Those 3 rectangles have areas 4, 8, and 12, which adds up to 24. This upper sum is too big. You guys following this, how this works? The trick is to create a step function with 3 steps. 3 steps is perfect for making the UP3 of f give us the right value for the integral. Okay? Of course, there's other answers, but this one's the easiest one. You can change these numbers and change the interval and all that. But the idea here is to use a step function. Okay. I bet the LP3 of f is a better estimate than the LP4 of f as well, for kind of the same reasons. You could also think about that as a, anytime I give you something like this in the review session, you ought to be thinking, gee, he might ask me about the other one on the test. So if I ask you about the UPF here, then a good thing to think about for yourself to practice would be the LPF. How would the question read for that? Okay, sounds good so far. Is everybody comfortable with this problem? Think you could come up with that? Thought about it? I know we haven't been doing this chapter 6 stuff for that long yet, but hopefully it gets a little more natural as we go along. Okay, let's look at the next question. Number 3 on the handout here. Okay, so number 3 is also asking for an example. So it says, give examples of 2 functions this time, f and g, that go from some closed interval a, b to r, such that f times g is Riemann integrable, but f is not Riemann integrable and or g, one or the other or both, are not Riemann integrable by themselves. So this is, the idea here is if you take a product of 2 functions and you get something that you can integrate, it doesn't mean that the functions you started with could be integrated. Does anybody know any example of a function that's not Riemann integrable? Where, so remember, you have this, we always know that this is true, right? The supremum of all the lower sums is always less than or equal to the infimum of all of the upper sums. But does anybody remember an example where we said that these are not necessarily equal? By the way, just as a total aside, before we have class on Monday, do me a big favor. I say this all the time. You guys are good students, so you know this, but please review your notes from the Wednesday lecture before, because it's been 12 days. It should just be good to read that over again. You'll find in those notes, I only did one example of a function that was not Riemann integrable. So it'd be good to think about that right now because we need an example. Do you remember it? What is it, Sarah?
Is it the recent function
Mm-hmm.
0 Riemann?
Mm-hmm.
If x is rational.
There we go. There we go. I forget which way I did it, whether it was this way or this way, but that's basically it. This is a good example. This function is not Riemann integrable. Every lower sum is going to equal 0, which means that the biggest or supremum of all of those lower sums is just 0. On the other hand, every upper sum is going to equal, b minus a, whatever your interval a, b is, it's just going to be b minus a. So the infimum of all of those b minus a's is just b minus a. So that's not equal to 0. So these are not equal in that case. Okay, so this is not Riemann integrable. So then the question is, we want to create another function that's, you have an idea already?
No, we're gonna switch. No,
What if you switch these? What if you switch these, right? If you switch these, basically, same thing. This lower sum, all the lower sums are 0, all the upper sums are b minus a, so these are not the same. But now what happens when you look at what is f times g? When you multiply these two functions together, what do you get? You get just the function 0, a constant function. Of course, the constant function 0, all of the big mi's and all of the little mi's are all 0. So all of the upper sums and all of the lower sums are 0. They all agree these values are both equal to 0. Exactly. That's the example. That's absolutely the best way to do it. Okay. And it doesn't really matter what closed interval you use. You can choose any numbers for a and b that you want. You don't have to get specific with the partition. You don't have to look at any particular example of a partition here, because it doesn't matter what the partition is. All the big mi's are 1 and all the little mi's are 0 regardless of what partition you use. Okay? It's there's a little bit of a theme going on here, guys, which is that, when you're looking at these UPFs and LPFs, let me just go back and remind you again, right? You have these formulas, and they kind of look like this. In some cases, to make these calculations simpler, in some cases we've been using this PN partition, which makes all of these numbers the same. All of these numbers become just b minus a over n, and you can factor them out of the sum. Okay, that works great. Another thing that you can hope for in some examples, depending on the function, is that all of the big mi's or little mi's are the same. Like on this problem, all of the big mi's are equal to 1. You can factor them out. All of the little mi's are equal to 0. You can factor them out. So I'm not saying you can always do this, right? There are going to be plenty of examples where you can't get away with anything very simple, but the idea is sometimes you can factor things out of these summations and make the calculations easier, right? So that's kind of the strategy that you can use there. Okay, everybody okay with this example? Is really the best example. I'm not even sure if I can think of another. There'd be other ways to make examples, but this is definitely the most natural way to get a good counterexample in there. Okay, let's go on to the next one. Okay, so the next one is the following thing.
I don't know if this is a problem, but
yeah,
her head is blocking.
Oh, who's Jenna's?
Yeah, a
okay,
little
Jenna,
bit.
could you slide just
Just
slightly? Just because I guess when I'm way over here on the left side.
Yeah.
Okay, thanks for pointing that out.
Yeah. Sorry.
Here, do you want to sit over here?
Yeah.
Just put this stuff down here on the floor. I'll slide my stuff out of the way here a little bit. Is that better?
Yeah.
Everybody can see, hopefully. Sorry to displace you like this, but much appreciated. Oh, yes. That's important too. Okay, so for number 4 here, let f of x equal x squared on the closed interval from 2 to 8. Okay, so just making this up. And then they want you to use the PN partition. So use PN to find U of PNF and L of PNF. We're going to calculate these two things. By the way, we know that this is going to be Riemann integrable. In fact, they do ask us over here eventually to compute the integral from 2 to 8 of f. We could actually, if we wanted to, we could do this part right now. Don't be expecting like lots of credit for being able to get this right, because I know everybody from Math 150A knows how to find an antiderivative and come up with the answer. That's not really the point, but I would like to know what I'm shooting for. So if we wanted to think ahead to the fundamental theorem of calculus, we could find an antiderivative for this, which we all know, 1/3 x cubed, and we could evaluate it from 2 to 8 and come up with an answer here. I think 8 cubed is 324, I believe. 64 times, is that right? No.
Smoother than-
No, it's the 512. 512, right? 8 cubed, yeah, that's 2 to the 9, 512. And then minus 2 cubed is 8. So we're gonna get like 504 divided by 3, which is what, 168? Okay, so that's what we're expecting. It's just the reason that we're not, showing off our Math 350 skills when we do that. But it's good to know what the answer is so that when we start calculating these things, we'll be able to see if we made a mistake maybe. Okay, so everybody's okay so far with what I've got up here. Okay, so just remember how this works. We've done a couple of these, and I also put up a video of another example. This is basically the interval, and you're chopping it into n equal pieces here, right? So just remember that x0 and xn are the endpoints of the interval. And then you have, x1, x2, and so on. Okay. So we actually have a formula. You're going to want to write this down anytime you do one of these problems. You're going to have the formula for the ith term, which really is just starting from the left-hand endpoint of the interval, which is 2, and you're going to add, well, however many, so there are going to be I widths of b minus a over n. In this case, b minus a is 6, so it's going to be 6 over n. So it's 2 plus I times 6 over n. You want to make sure you can write that down, and that's for I. I could be 0, 1, 2, all the way up to n. Just check that works, right? So our delta xi is just the 6 over n part, right? b minus a over n. We have those values there. Okay, so for example, when I'm doing my upper sum here, this is just the summation, big Mi times delta xi. I know that all of my delta xi's are equal to 6 over n. So I can actually pull that out, and then I'm simply going to sum up the big Mi values from 1 to n. So far so good? So now the big Mi values, let's see. This is x squared, right? So when you think about the function, it's a parabola. Over here is like 0, 0, and then the parabola goes up. And this is a very bad picture, but in the idea here, what's going on. So what can you tell me about the big Mi's based on the nature of the function?
Increasing.
Right, because the function is increasing, the big Mi's are the right-hand endpoints of each subinterval. So for example, big M1 is just f of x1. Big M2 is just f of x2, which just means you're squaring those x1, x2, x3, and so on, those values, right? So this is actually just going to be xi squared that you're adding up. So we're summation from 1 to n of 2 plus 6i over n squared. That's what it's going to be. This is just taking f of xi. You're taking xi and you're squaring it according to the function. Right? So that's what you're going to end up with. Okay, so this is going to take a little bit of a calculation. So keep this 168 in mind. I'm going to write it down over here. That's the answer we ultimately are hoping to come up with. But let's take a look at the rest of this. By the way, you might be wondering, you might be thinking, this is an increasing function. Can't we just do remember the problem earlier where we did the subtraction here and we saw all the cancellation? You're right, there is going to be that same cancellation again here. The only reason I'm not utilizing that is because the question actually asks me to find these numbers. If I only take the difference, then I'm going to lose what the actual values of these are. So that's why I'm actually calculating this rather than just canceling off the LPF frontage. So that's, but you could do this, of course, if you were trying to prove that the function was Riemann integrable. But at this point, what I'm trying to do actually is calculate this value. So to do this, what you're going to want to do is actually square out, FOIL out this expression here. So we're going to have a summation from 1 to n. 2 squared is 4, plus 2 times 6i over n, that's what, 24i over n. And then plus 6i over n squared, which would be 36i squared over n squared. So we just literally squared this thing out that was in the brackets there. Okay? Okay, let's keep working on this. Summation I from 1 to n, we have a 6 over n out in front. We have 4. Well, actually, let's just, how do I want to do this? Actually, sorry, I'm going to back up. Let's just do each of these 3 parts. If I take 4 plus 4 plus 4 plus 4 n times, how much does that give me? 4n, right? Okay, and then plus, now here we have 24 over n, which is just a constant, times the summation of I. So I'm just going to put that right there. And then here we have 36 over n squared times the summation of I squared. Okay? So this is the expressions. Okay, so we have 6 over n, and then we have 4n, and then plus 24 over n. Now, here's where we're going to need to learn a few values. I did this one in class before the break. It's been 12 days. But do you remember if I add up 1 plus 2 plus 3 up to n, what that gives me? There you go. N times n plus 1 over 2. You're going to want to know that value. Okay, very good. And then plus 36 over n squared. There is a formula for the sums of the squares as well. So this would be 1 plus 4 plus 9 plus 16 and so on.
2n plus 1, 2n plus 1.
It's n times n plus 1 times 2n plus 1 all over 6. 6 is right. You either know it or you don't. Okay? Now you know. If you didn't know it already, now you know. The formula for the sums of the first n squares is n times n plus 1 times 2n plus 1 over 6. We haven't seen that one yet in class, but that is the value there. I'm not going to give you one on the test that you haven't seen before. I might expect you to know this one because we just used it right now. But you know, you're not going to get like an I to the 8th power and be asked to find the sums of those. That would be a little bit crazy. Okay, now we should be able to start simplifying some things. Okay, so let's see what we can do here. So let's just do this first part. I have 24 and then n divided by n. So that's just 24. All right. Now here I have a 6 and a 24 on top and a 2 on the bottom. I believe that comes out to 72. And then what about the n stuff? Well, I have an n on the bottom here canceling this n. Or I can just cancel these two, I guess. Then I have an n plus 1 over n. So n plus 1 over n. All right, and then what else do I have? I have a 6 canceling with a 6. And there's an n here that cancels with one of these n's. So this is actually going to give me 36 n plus 1, 2n plus 1, all over 6, I believe. No, all over n. Sorry, I already canceled the constants. So there's the expression.
N squared? Because there's the one n on the outside.
So I have an n here. Oh, n squared. Yes, n squared. Thank you. N squared there. Exactly. Does that look okay to everybody? Just for my own benefit. Okay, this would be a final answer, actually. This is perfectly fine. It's a closed form formula, and perfectly good. If n gets really, really big, what happens to this number? So as n goes to infinity, I just want to know, this part, of course, is 24. What happens to this term when n gets really big? 72. Because this is really just, this is approaching 1 times 72. Good. Okay, and then what about this term when n gets really big?
0.
No.
2.
Yeah, but this part approaches 2 because you have 2n squared over n squared, but then it's multiplied by 36. So this term is 2 times 36, which is also 72. What are you going to add all that up? 168. Oh, that makes me feel good. So that's the number I'm looking for down here. Okay. Okay, so that looks pretty good. That looks pretty good. Does that make sense, guys? Okay. So the point then is that that's the value of UPN of F. Okay. So just to reiterate this again, the upper integral of F, right? This is the infimum of all of the UPFs. Well, here are some of the UPFs. So the smallest of all the UPFs, which is what this is, has to be less than or equal to that. So this is less than or equal to whatever this is, 24 plus 72 n plus 1 over n plus 36 n plus 1. I'm trying to just explain how the argument is going to work here. So this expression is greater than or equal to the infimum of all of those upper sums. On the other hand, of course, we proved that the lower Riemann integral is always less than or equal to the upper Riemann integral. And for this one, of course, this will be greater than or equal to any LPF that we look at. So in other words, the lower sum would be less than or equal to that one. And I think maybe just because this has been going on, we've been talking for a long time, I might just give you the answer. Basically, the LPN, because it's an increasing function, to calculate the LPN of F, you can basically take the formula for the UPN of F and get rid of the last term, which was the biggest term, and throw in the left-hand term here as well. So subtract off whatever this last term would be, 8 squared, basically, times 6 over n. And then, so this would be u of PNF minus 8 squared times 6 over n. And then we add on 2 squared times 6 over n, basically. But the point is going to be that as n goes to infinity, of course, these denominators blow up. We basically get that these two things are going to the same value, right? They're both approaching the same value. And what common value is it? Well, 168, right? That's what happens as n gets big. So therefore, everything in the middle gets sandwiched to that same value. This is the argument I think I showed you on a linear function in class. This is a little harder because it's quadratic. So it's messier. But the strategy for proving it is still the same. You use the PN partition, you get an expression for UPF, you get another expression for LPF, you show that as n gets big that they converge to the same number, so that then these inside values also have to converge to that same number. That's the idea. Make sense? So I didn't actually do the LPF calculation, but it's very similar to the UPF calculation. Okay, and I have all these typed up in detail too, so you can always check them later on. Is this making reasonable sense? How are we doing on time? Just 5:40. Okay, great. Okay, perfect. Yeah.
Dr. Anime, if you were to have f of x equals x squared plus a constant, so where you have u of PNF, and then all the way to the right where it says 6 over n there, you don't have plus that constant outside of the brackets?
Yeah.
Okay.
Yeah, exactly. If it was like x squared plus 1, it would just be a plus. It would be a plus 1. It would be outside of these brackets, but it would still be inside the summation.
Right.
So that if you did the summation n from 1 to n, this plus 1 would magnify and become a plus n. Yeah, exactly. Okay.
It doesn't matter if we put the subscript n with
the
lower
P?
sum. Yeah.
You should. You mean this part here?
Yeah.
Yeah, you really should, because that's the partition you're working with.
Okay.
Yeah, try to get in the, don't just write L of P, F.
But if we said use P to find.
Use
instead of
Pn.
Pn,
Use Pn to find this and then the LPn of F. I think that's what it says in the question, right? They want you to find the L of Pn F. So you should use that notation. Yeah. Does this make sense? So basically, if I talk about Pn, I'm always talking about this partition that chops the interval into n equal pieces. We're going to use that a lot. Okay. Okay, let's go on. Might do 1 or 2 more of these and then just call it a day. But we've done a lot. Let's go on to number 5. Okay, this is a nice little problem. So our number 5. So let's see. So suppose that f is Riemann integrable on the closed interval AB, and then c is some real number, and then we're going to define a new function g, and g is actually going from the interval a plus c to b plus c. So it's not the same domain. It's not the same domain. The formula for g is g of x is defined to be equal to f of x minus c. So this is our formula for g. And then we want to show that g is Riemann integrable from a plus c to b plus c. Okay. So to be a little clear what's going on here, we have the interval from a to b. We have some function f here. And then a plus c to b plus c might be looking like this. The c is basically shifting the domain, right? And then you have a new function g. However, to evaluate g, for example, what is g of a plus c? Well, it's just f of a. If I put in a plus c for x, I just get f of a. So in other words, it's the same values that we had there. And what is g of b plus c? It's just f of b, right? And then all the points in between are just the same point. So it's basically just a shifted graph. It's the same graph as the original one, it's just shifted. You guys do this all the time in your basic algebra classes. They try to teach the high school kids. You add c here, it shifts the graph to the right by c units or whatever. So that's kind of what's going on. Well, it makes sense that if this one's Riemann integrable, you can find this area, then you should be able to find this one too. Okay. So when we're proving that g is Riemann integrable, though, what comes to mind in terms of your approach? How do we prove that something is Riemann integrable? Are we going to actually show that the upper Riemann integral equals the lower Riemann integral by doing the supremums of all the lower sums and the... We need to use the theorem, right? Whenever you're being asked to show that a function is Riemann integrable, and I realize, guys, I really didn't quite cover this in time before our break, but this is going to be really critical. So I'm going to be talking a lot about this on Monday as well. Theorem 6.2. That's the one that says that a function is Riemann integrable if, for all epsilon, you can find a partition such that UPF minus LPF is less than epsilon. Okay, so to do this, the first line of the proof, as is so often the case this whole semester, the first thing we write down is let epsilon greater than 0 be given. Our job is to come up with a partition of this interval such that U of PG minus L of PG is less than epsilon. We need to find a way to partition this interval right here. Okay? Using the fact that F is already Riemann integrable. Anybody have a suggestion how to get this thing off the ground?
Can we use the Pn again here?
We can. We certainly would be able to do that. How are you going to figure out what n to use?
Could it be any n? Or do we have to choose a specific one for this
The
problem?
trouble is somebody could give you a really small epsilon and then you try to use n equals 1, for example. Means you're going to chop it into one giant piece.
Right.
I'm not feeling very good that the U P sub 1 of G minus LP1 of G would necessarily be less than this epsilon could be tiny, right?
Right.
Part of our problem too is we don't know what the function, we don't know how bad these functions are. This is a very abstract problem. So when we're using the, I'll get to you in just a second, I know you have an idea. When we're using the P sub n partition, like on the last problem, we had a specific function, right? We had a specific function. We were able to like do some tedious calculation and figure out what n should be. And that's great when you have a lot of specificity. You know what your function is. Here, this is just so abstract. I don't know what f is. I kind of drew an example here, but I really don't know what the function is. You have an idea?
Would it be the n that works for f since it's already a Riemann sum?
Okay, f is already Riemann integrable. So by theorem 6.2, given this epsilon, there already exists a partition. We don't even have to call it P sub n. We just call it P. It's just some partition. By theorem 6.2, very good. By theorem 6.2, since f is Riemann integrable on AB, there exists a partition, P, this is a partition of AB, such that UPF minus LPF is less than epsilon. We can do that. And by the way, when I say here that UPF minus LPF is less than epsilon, I should clarify, UPF minus LPF is less than whatever we want to make it. Right? Maybe we'll find out later that we want to make this epsilon over 2 or something like that. Okay, we'll see later on. As it's going to turn out, we're not going to need to change the epsilon. This is going to be the right epsilon. But you can actually put whatever you want right there. Okay, so in other words, we have this partition here. We have this partition up here. We have, I'm not even going to necessarily think of it as a piece of n partition. We have some partition up here such that UPF minus LPF was less than epsilon. Unfortunately, we need to come up with a partition. Let me just draw this a little better. So here's my partition P, which is a partition of the interval AB. We need to come up with a partition of the interval A plus C to B plus C that we can work. We need to create this partition. So we are given this partition. In fact, let's do this. Let's write our partition P as x naught, x1, x2, dot, 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 up to xn. I don't have any idea what these points are, but let's just say that's what they are.
Is this LPF, not G?
Oh, I'm sorry, this is LPF. Oh, jeez. Sorry, it's been a long break. Okay, I didn't get much sleep last night. Yeah, UPF minus LPF less than epsilon. Very good, thank you. Little correction there. Okay, so we have this partition of some points. We don't know where they are. But we need to come up with a partition of this interval. Does anybody have a suggestion how we're going to get the partition of the interval A plus C to B plus C?
Can we add C?
Say again?
Can we add C to each one?
Just add C to each of these, exactly. So here's what I'm going to suggest we do, guys. Let me call it P sub C, just so I have a notation here. P sub c, which is going to be the set x naught plus c, x1 plus c, dot, 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 all the way up to xn plus c. This is a partition of the interval a plus c to b plus c. Okay? So we form that. So really, what you're doing is you're just taking all these points and adding c to them. So what that does is it gives you a partition that is pretty much these points just shifted. Makes sense, doesn't it? That probably is going to work. Because when you now calculate, so here's the point, guys. When you calculate this difference, the new partition with the new function g, right? What are you doing here? You're doing these upper sums and lower sums, big mi's times delta xi's, and then subtracting little mi's times delta xi. These big mi's, right? The big mi right here, whatever the big mi is here, I guess it's that endpoint, is going to be the same as the big mi there, right? It's the same number. Look, the function f and g, they are not shifted up and down at all. They're only shifted left and right. So the vertical height, the y value is not changing. And the delta xi's, all of these delta xi's are also the same. So do you agree with me then that this is just the same as UPF minus LPF? Okay, again, remember, what are the formulas here? Let's just look at the UPF. Here's the formula for UPF. In order to calculate this, I have to know the big mi's and the delta xi's. When I switch to the UP sub c of g, the delta xi's don't change, right? The widths of each subinterval doesn't change because all you've done is added c to every point in the partition. And the capital M's are not changing because the functions are the same. On each subinterval, the maximum height, the supremum values and infimum values, they're staying the same. So this is the end of the proof then, because this part was already assumed to be less than epsilon. So you created your partition and you got your value. Does this make some sense? Yeah. So that is how you can do that calculation. Now, there's a second part to that question. I just want to say one quick word. So we showed that G was Riemann integrable here. Then there's a second part to that question, which is asking you to show, that the actual value of the integral. So once I know that G is Riemann integrable, well then this makes sense. And they're asking you to show that that is the same value as the integral of f from a to b. Okay. So just a quick little word about how to do that. Essentially what you want to do that is subtract them and look at the absolute value of the difference. Okay, you essentially want to do a quick little subtraction here. So if we look at the integral of g from a plus c to b plus c, and we subtract the integral of f from a to b, if we look at that, if we look at how much that is, well, both of these numbers are between UPF and LPF. So in other words, my point is that this integral of g, whatever it is definitely less than or equal to u of p sub c of g. Just put this. So in other words, because remember, how is the integral defined? It's the infimum of all the upper sums. So right now I've just made whatever this integral is, I've just made it bigger. I've replaced it with a larger number because the actual integral is the infimum of all of these upper sums. Okay. On the other hand, this integral is the supremum of all of the lower sums. So if I choose to subtract less than I'm currently subtracting, so this is the supremum of all the lower sums. Well, here's a lower sum. This lower sum is actually a smaller number than this. I'm actually now subtracting less. So I've got a bigger number here and a smaller number here. When I subtract them, it gets bigger. That's why I'm justifying this inequality. I've made this thing bigger and I've made this thing smaller, so that the difference has actually gotten bigger. Guys get that? But my point is, of course, the point of that is, however, that u of PCG, right, that's just the upper sum right here with this function. Isn't that just the same as u of PF? Because all you've done is shifted, it's the same graph, it's just shifted. So this is actually just u of PF minus L of PF, and at this point you realize you don't need the absolute value bars at all, and this is less than epsilon. So how far apart are these two numbers? They are less than epsilon apart, and what's epsilon? Some arbitrary number, right? Of course this is at least 0, by the way. So this is at least 0, but it's less than epsilon. Epsilon is arbitrary. Make it as small as you want. Can these two things that we're subtracting be non-zero when I subtract them? No, because then I could just pick an epsilon that was smaller than that difference. So since this is true, so since this holds for all epsilon greater than 0, remember epsilon was arbitrary, right? Since this holds for all epsilon greater than 0, we must have the integral from a plus c to b plus c of g equal to the integral from a to b of f. They have to be the same. If they're not the same, then we have a strictly positive number here, and I could just come along with an epsilon that was smaller than that and contradict this chain of inequalities. That's really what's going on. The trick here is really this first step, again, to remember that this integral can be replaced by something bigger than it, and this integral can be replaced by something smaller than it, resulting in a bigger difference when I do the subtraction. Does that make sense? Okay, nice problem. It's kind of obvious, you look at the pictures, yeah, of course, this all should be true, but this is how you have to write it up, how you work it all out. Okay, I am going to skip number 6, I think, for now. Let's go on to number 7, and then I think maybe we'll call it a day at that point. Hopefully it stopped raining. Are these some good practice problems? Getting this stuff in here. I'm glad you guys came today. This is a good chance to get a jump on, especially this integration stuff. Okay, so number 7. Let's see. So we have f from a to b, from the interval a, b to r, I'm sorry, and this is continuous. And f of x is greater than or equal to 0 for all x in the interval. So x is always, or f of x is always at least 0. And then it says assume that f of c is equal to 1 for some c in the open interval ab. Okay, and so then there's 2 parts to this. The first part is they want you to prove that this integral, by the way, anytime you're writing this symbol down, if you're writing down the symbol integral a to b to f, you're basically saying f is Riemann integrable. If f is not Riemann integrable, then this technically is not defined. So I'm being a little sloppy in writing this down so quickly, but the fact of the matter is that every continuous function, I haven't stated this formally in class, but every continuous function is always Riemann integrable on that domain. So this symbol does make sense, and what we're going to do here is prove that it is strictly positive. Strictly positive. Does it make sense that that should be true? Really have to, make sure the intuition is working right for you. Here's your closed interval AB. The function is always at least 0, but somewhere along the line there's a C value. Here's a value of 1, and the function is continuous, so I have to be able to draw this graph without picking up my pencil. So even if the graph is like really close to 0 here, it eventually has to get up and tag this point. And what happens, of course, in doing that is you create for yourself a little bit of positive area. That's what you're expecting here. Okay, so it's reasonable to think that this would be greater than 0. Okay. Okay, so we want to try to prove this now. We're not being asked to find the value of the integral. We really can't do that because we don't have a function. We don't know what the formula is for f. So it doesn't make sense to do that. But we can recall, what we want to remember here is that this integral is just the common value. You know, it's this common value of the upper and lower Riemann integrals here. So remember, this one is your supremum of all of your lower sums. And this one is the infimum of all of your upper sums. Okay, so we have that. Anybody have any thoughts on how to maybe do this? And by the way, you're going to see in part B of the question, which we aren't getting to yet. Part B says, show that this is not true if f is not continuous. We have to use the continuity of f here. F is continuous. F is a continuous function, so something like this. Got to hit this point 1, y value of 1 here. I know that all of my big mi's, all of my little mi's, they're all at least 0, because the function is always at least 0. So you're adding up a bunch of numbers that are always 0 or more. Any thoughts how to do this maybe? I'm going to draw this picture a little bigger because I just don't know that it's going to be, people can see it very well on the back there. So let me just draw the picture one more time. Here's 1, and I'm just going to exaggerate it a little bit more like that maybe. So even if the function tries to be 0 for a long time, it has to shoot up somewhere here.
So like an integral where you'd have
So do you guys agree that there has to be a neighborhood around C where the function is above 0? In fact, we could even take an epsilon of a half. We could build an epsilon of a half here, right? And we could say that, well, given epsilon of 1/2, so for epsilon equal to 1/2, there exists a neighborhood, a delta, basically, such that if x is in, C minus delta to C plus delta, then f of x is, well, be between 1/2 and 3/2 if I choose this epsilon, right? So in other words, f of x minus f of c has to be less than 1/2. But what does that really mean? F of c is 1. So in particular, what we can say is, I don't need to say the whole thing, I just need to be able to say that f of x is at least 1/2. Throughout this blue neighborhood here, this is my neighborhood here, if I go up and I look at my graph, my graph is always above 1/2. Okay, does this make sense? So, does that help me figure out how to do this?
So at least your supreme, or
So your lower bound would be your supremum, and that's got a
See, okay, do I want to work with this side or with this side? And we know that they're going to be equal. But this one or this one? If we're trying to prove the integral is greater than 0.
small one.
Yeah, see, because let's say I tried to compute an upper sum, and let's say I got a positive upper sum. That's not going to help me because, okay, great, you found a partition that gave you a positive upper sum, but the infimum could still be 0, right? So what you'd rather do is find a lower sum. All you have to do, guys, here's the thing. All you have to do is find one lower sum that is positive, because the supremum of all of your lower sums will be at least that much. This is what you're trying to prove, right? So and this is the same as that. These are equal. So if I can just find one lower sum that is positive, then my supremum of all of those lower sums is positive, and I'm done. We don't want to work with the upper sums here. Doesn't help us. Because yeah, if we find an upper sum that's positive, great, but there could be another upper sum that has a smaller value, and maybe the infimum is 0. It doesn't give us what we want. Okay, so we need to find a lower sum. So, but this is really neat because I only have to find one partition now. Can somebody suggest how to partition this interval so that I end up with a lower sum that is going to be positive?
A and C minus delta.
Consider P equal to A, C minus delta,
C plus delta.
C plus delta,
B.
and B. Take that partition. Okay, now if you look at, let's calculate the LPF of that. Right? You're going to have 3 terms, right? You're going to have little m1 delta x1 plus little m2 delta x2 plus little m3 delta x3. I have no idea what the first and third term are, other than the fact that they are positive. Well, at least 0. This is at least 0 right here. And the third one is also at least 0. Why is that? Because the whole function is always at least 0, so these little m's are all at least 0. But the second term, which is the little m2, that's this subinterval right here. Do you see that the little m's, the little m2 I should say, is at least 1/2, and the delta x is a positive number. The point is, this one is strictly positive. Is strictly positive. So you have a number that's at least 0, plus a number that's strictly positive, plus another number that's at least 0. That adds up to a strictly positive amount. Isn't that cool? Okay, so you've actually shown then, that 0 is less than L of PF, which is then less than or equal to the supremum of all of the LPFs, which is the integral of the function. So there you go. It's strictly positive.
It's actually what comes out to be delta, because it's 1/2 times.
Yeah, it's actually 1/2 of whatever. Yeah, 1/2 of 2 delta. Yeah, which would be delta. Right, this actually comes out to delta. Yeah, exactly. Well, actually, I shouldn't say that. At least delta, because these values, the little m2 value is at least 1/2. It could be more. Yeah, that's true. Okay, isn't that nice? Wonderful little argument there. So the idea is show that one specific LPF is positive, then the integral has to be more than that, right? It's greater than or equal to that. So you're working with the L's here, not the U's. Now you can imagine, okay, you can imagine a test question after you see this one. Okay, somebody's going to give you a -1, right, and say show less than 0, right, turn everything around. Now instead of the L's, you're going to be working with the U's, you see. These are the things that, you know, you can think about. I mean, I don't know what I'm going to ask on a test, but this is the kind of thing I like to do, is take an idea you already saw and give it to you again, but in a slightly different format. Okay, there's a second part to this question. And then I think we'll just call it good and leave the last problem for another time, maybe. Just let you read it, maybe. So part B says, show that what we just proved here is not true if f is not continuous. Okay, so A fails if f is not continuous on this interval. So if A fails, then what do you think the value of the integral is going to be? Or, of course, if it's not continuous, then maybe this doesn't even make sense anymore. Let's assume it does make sense. Let's assume we still have an integrable function. But what would the value of the integral have to be if this isn't true? The function is still greater than or equal to 0. It has to be 0 then, right? So in other words, what we're saying is, okay, so here's your interval AB. The function is still greater than or equal to 0, and there is still a point where f of c is equal to 1 here, right? But the function is not continuous, so it should be possible to come up with a function now that hits this point and is always above the x-axis, but where the value of the integral is not greater than 0. So we would expect the value of that integral to be equal to 0. It can't be negative, because look at your function, right? So it says give an example. So it says show, that means it wants you to give a function. Can we give a function here?
X equals 0 if x is not equal to c.
Exactly. Great, so f of x, let's make sure everybody got that, is equal to 0 if x does not equal to c, and 1 if x does equal c. Right? It just jumps. Obviously, that's not going to be continuous. Okay. Does that make some sense? The point here, guys, is with that function, for every partition of the interval AB, for every partition, what's the lower sum going to equal? Doesn't matter how you chop this up, the little mi's are all 0. So when you add up those little mi's times those delta xi's, you of course are getting 0. So if every lower sum is 0, then what would be the supremum of all of those lower sums? The supremum of a bunch of zeros is just 0. So your integral is just 0. Your integral is just 0. Yeah. It's not strictly positive anymore. We're going to have another theorem. Again, I keep going to things we haven't done yet. But we're going to have another theorem that says if you take a function and you just move one point up or down, the value of the integral doesn't change. So you can imagine this function is really, you started with the 0 function, which of course has a value of 0, and you moved one single point away from 0, it doesn't change the integral. The integral is the same value that it had before. So that's a theorem that we have to discuss here in these last couple weeks. But, does that kind of make sense, guys? Okay, well these are some good practice examples with integration, a lot of integration stuff. We did some mean value stuff earlier on, uniform continuity, lots of good stuff to study. I think I'll leave it at that for now. I'm hoping that, I don't know how you guys are coming along on the homework. I think that's obviously, we want to get that done by tomorrow, obviously. Right, Monday, I guess it is. Today's only Saturday. So, you know, try and get those problems out of the way. And, you know, when you're tired of working on the homework, go back to your flashcards again, review some definitions and theorems. read through your notes. Please do read through those notes carefully, especially the integration stuff before Monday's class, so that you're on top of that. I think I'm gonna call it good. So, does anybody have any questions about any of that? Kind of a long session tonight, but figured it was good to practice a little bit more. I haven't seen you for a while, so it'd be good to do several examples. Okay, we'll see you guys again soon then.